During the design of external pressure vessel, after preliminary design calculation, if the design is not adequate, means calculated allowable pressure is less than the design pressure, operating pressure, then how to proceed? Let us see. Let us explain the stuff with the help of practical design examples. The detailed description of such examples have been illustrated in the previous videos. Link in the description, you can follow them and can learn the procedure as well. In the first problem, we have a cylinder with length of 15 feet and the outside diameter is 10 feet, and we have to design it for 10 psi respectively. Now we have arbitrarily suggested a thickness of 3 by 8 inches. You can choose another one and then solving for d naught by t and L by d naught and finding out from graph. And the resultant calculated allowable pressure for this thickness is 10.9 psi. Here a check is needed to ascertain that the buckling is in the elastic rather than the inelastic region, and this is made. So in this example, allowable pressure is greater than the design pressure. The thickness is suitable if we exclude other safety factors. Now in the next example, we will see the design with stiffening rings. We have to design a vessel with 15 psi external pressure and the outside diameter is 96 inches and tangent to tangent length is 576 inches and the head type is 2:1 ellipsoidal. Material of shell is SA285C and the modulus of elasticity of the material is given at 50° F. Now we are starting the solution. In the first step, 1/3 of the depth of the head of the cylinder is added to tangent length of the cylinder as recommended by the design criteria previously mentioned. We can apply the following relation for the ellipsoidal heads. The new design length is 592 inches and 16 inches added to 576 inches. You should also consider this practice in the previous example. In the very next step, we have suggested a thickness, a starting thickness of 1/2 inches and calculate d naught by t and L by d naught and finding factor A from the chart. The allowable pressure, the maximum allowable pressure is 6.5 psi, which is less and inadequate than the design pressure. Now in such a situation, there are two ways to proceed. The first way, either bump up the shell thickness to the next thickness of the plate available in the market and perform whole calculation until and unless we reach a desired design condition. But going this way, we can face the following issues. It becomes too expensive to construct a vessel with a more thick plate. Weight may become too high. Very thick sheet means overall high machining cost. The second way is to add the stiffening rings to the vessel. The stiffening ring will reduce the L dimension. If the option of adding stiffening ring is selected, then the spacing can be determined to suit the vessel configuration. The thin cylinder may be stiffened with the help of longitudinal stiffeners, also called stringers or string stiffeners. A combination of stiffening rings and stiffening strings can also be used on a very thin shell. How the stiffening rings reduce the necessary thickness needed. Stiffening rings, flanges and so on are supposed to be acting as the lines of supports. These supports are assumed to carry all the load that the shell carries due to external pressure. Actually, in deriving basic equation for external pressure vessels, shell is assumed to be simply supported from ends, and this is assumed to be true for stiffening rings, flanges or any other stuff like this supporting the shell, just like simply supported vessel or shell. Here stiffening rings are dividing the shell in three sections. The end section of 200 inches and the middle section of 192 inches. So the L dimension is reduced from 576 inches, that is the original length of the shell, to 200 inches and 192 inches in the respective sections. Therefore, following the addition of stiffening rings or other like stuff to the shell can be seen as a shell virtually dividing in relative sections on relative position to the L dimension. Furthermore, every one of these segments behave like a different shell, which consequently impact the mathematical outcome of the equation. Here's an example of distillation column. The same column is stiffened and unstiffened. The unstiffened column needs more thick plate, while the stiffened least. In spite of providing various other functions, flanges are also providing structural support. Like stiffening rings, and will be considered as stiffeners. And each one of its segment is with reduced L dimension, and a model of reactor here is shown, also has the flanges, and in the middle, the torus-like structure, and these are all providing functions like stiffening rings. Stiffening rings can also be placed internally. Stiffening rings can also be placed simultaneously internally and externally to the shell. Here, there are some other types of stiffening rings used in industrial fabrication. Let us back to ongoing design problem, as the selected thickness is insufficient for the shell. So while choosing option 2 and adding stiffening ring to the vessel, angle type of stiffening ring are being added. These stiffening rings are dividing the vessel in three sections at relative position. Now in each of these three sections, every section will be treated separately and will be evaluated for the design pressure or external design pressure. Now we will perform calculation as shell has been divided in three sections and the length of sections 1 and 3 is of 200 inches and the length of middle section is 192 inches. By calculating L by D naught and D naught by T and determining the factor I and B from charts, we can see that the overall allowable pressure is 20.8 psi.